Hello everyone, this is Dr. Priya Hassan. Today we'll be talking about the Milky Way galaxy. As you've seen in this course, our definition of home has been increasing, right? We started off with the Earth, the solar system, stars, and now we are moving on to the galaxy, our home galaxy, which is the Milky Way. If you go to a dark place, which is not what happens if you belong to a city, but if you go to some place in the outskirts, you would actually see on a dark sky, you'd see a nice band of light that you can see, which is actually the band of the Milky Way, right? It appears to us as a large band like this because we are actually within the Milky Way. And it is what we can see of the Milky Way while we are inside it, right? Historically, Professor Hassan has already spoken to you about how our perspective has increased. Like I started off with the geocentric view of the universe, then we moved on to the heliocentric view, and then the work of Herschel, and then you come up to the Shapley-Curtis debate about many galaxies, and now we have evolved from our understanding of the universe as belonging to literally a universe of galaxies, right? And galaxies have been already defined to you as large collections of stars, dust, and gas, which have a typical mass of about a billion to 100 billion, 1,000 billion rather, of the mass of the sun. So typically you would have a mass of like 10 power 42 kgs of a galaxy. Our Milky Way galaxy has a size of 30 kpc. And if you remember, we've already defined what are parsecs. And a parsec is approximately 3.26 light years, where a light year is the distance traveled by light in 1 year. But let us actually see how did we discover this picture of our galaxy. It's not easy, for example, if you live inside a building or inside a house, to actually make a picture of the house to which you belong to. And hence, this is quite a laborious task. Amongst the early studies were done in 1781 by Herschel, where he actually tried to reveal the shape of our galaxy. Now, what Herschel did is he made in a rough approximation that all stars are equally bright. And in that case, if they are equally bright, depending upon their faintness or their brightness, he measured their distances, assuming that all of them are equally bright. This assumption is not it's absolutely wrong, but it actually helped him to estimate the distance to several hundred stars. And this was the approximate map of the universe which he got, the galaxy, which he thought was the universe. Then we moved to 1920, where Shapley was at Mount Wilson Observatory, from which he could actually observe a whole lot of globular clusters. So you have an image over here. This is what a globular cluster is. It's a dense conglomeration of stars. Now, in globular clusters, there are certain kind of variables called Cepheid variables. And Cepheid variables have a peculiarity that they show a certain period luminosity dependence. So actually Cepheid variables can be used like what are called standard candles to find distances. So what Shapley actually did was that he actually used the Cepheids in these globular clusters. There were 93 of them, to which he actually could find out the distance using the luminosity period relationship by Henrietta Leavitt, which has got rubbed out over here, but that was done by Henrietta Leavitt. And you can see that what Shapley got was pretty good. You can actually see he got it that the sun was not in the center, it was off center in the galaxy. We don't belong to the center of the galaxy. And he got these distances to these various objects, right? So, but there was a slight mistake, a very big mistake that Shapley was making, and that is because of the not consideration of what is called extinction. Now, our galaxy, like I mentioned earlier, also contains a lot of gas and dust. And what gas and dust does is that it actually reduces the brightness of stars or galaxies. And therefore, what happens is a star which is a brighter one actually appears redder. That is you actually have the dust re-emitting in the infrared or in redder wavelengths. And therefore, objects which are brighter may look slightly dimmer due to the effect of extinction. And extinction is a very large quantity. So you can actually see that the diffuse interstellar dust in the plane of our galaxy causes an extinction of about 1 magnitude per kpc. Okay? And if you ignore the effects of extinction, you'd obviously misjudge distances by great amounts. And that was the basic mistake that Shapley had made in his estimations of the distances, because he had not considered extinction. He had not considered the effect of the gas and dust in the galaxy. So if you actually now, here I have a picture over here of, now that we know the structure of our galaxy, what Herschel revisited was just looking at this smaller part of this thing. And therefore what happens is, because of the extinction errors, the early estimates of our galaxies, sizes, it actually differed very widely. So Capitan actually did it, and it gives this. And Shapley, what happens is that because he did not consider extinction, he got a much larger size of the galaxy. He actually got the diameter of the galaxy to be 100 kpc, right? And using the globular clusters. Now the modern estimate, which I have over here, it actually shows us a 30 kpc size of visible stars. And Shapley overestimated it because he overestimated the distance because of not considering extinction. Okay. So another important thing we need to remember is that not everything is visible. In the sense, our eyes are very good detectors, but they only detect optical light. So we already spoke about what is called the electromagnetic spectrum, which you can see a whole range of wavelengths over here. This is from high frequency, shorter wavelengths, that's gamma rays and X-rays, to longer wavelengths, that is, here you have the infrared and the radio. Now, our eyes are detectors which can only detect a very small window of the electromagnetic spectrum, which is the visible light. And the problem in this is that because of the ability of the light, right, we actually miss out on different physical processes. So different physical processes which can be used to study objects, they actually emit in different wavelengths, which could include radio, X-ray, gamma ray, etc. Right? So if here I have a picture of a galaxy, the Whirlpool galaxy, in various wavelengths. So what you can see is that the radio emission, this is an image of the Whirlpool galaxy in radio. You can see that radio emission basically comes from cold gas. So if you want to study the cold gas in a galaxy, you need to see it through radio. Similarly, infrared emissions. The infrared emission is coming from cold stars. So cold stars in the galaxies are going to emit in the infrared. Optical are the solar-like stars. Ultraviolet is going to be very hot stars. And X-ray is going to be very hot gas. And therefore, if you want to make a complete study of the galaxy, you would actually require to observe the galaxy in various wavelengths. Because if you only observe in the optical part, you'll only get the stellar component of a certain set of stars. You will not get the colder stars and the hotter stars, which belong to the infrared and ultraviolet respectively. And hence, multi-wavelength astronomy, that is observing the galaxy in various wavelengths, is very essential to see the other components of the galaxies, which will emit in different wavelengths. So here I have an image which actually shows you multi-wavelength data of Milky Way using various wavelengths. On the top, you can see the radio continuum. This is in the 408 megahertz. You can see this is an image of the galaxy. This is an H1. Then you have the far infrared, near infrared, optical, X-ray, gamma ray. And like I mentioned earlier, there are different components of the galaxy which will emit in different wavelengths. And therefore, to study different components of the galaxy, we need to look at the different wavelengths which are in here. So I would also get your attention that when we show images of this, it's basically this point and this point which actually connect, and they form the disk of the galaxy, right? So you have got to think of these flattened out images as somehow being attached from the sides, right? From the sides over here, this to this. Now, what is the galaxy made of? Like I mentioned earlier, the galaxy is made up of stars, stellar remnants, clouds of gas and dust, hydrogen, helium, heavier elements. And therefore, like I mentioned, you need to see the galaxy in various wavelengths to study these different components of the galaxy. Now we'll just jump a bit in time and let's come up to our present understanding of where the sun lies in our galaxy. So if you consider this as our galaxy, the Milky Way, obviously this is not an image of our galaxy. We've never gone so far from our galaxy to take such a picture because we are very much inside the galaxy. But you can see that the sun does not belong to the center of the galaxy, and it's neither at the edge. It's about 2/3 out away on a spiral arm, right? It's actually on the edge of a spiral arm. So you can see this is where the sun is. I have another picture over here which shows you that this is our galaxy. The Milky Way galaxy is a spiral galaxy. You have heard about the different kinds of galaxies. It's a spiral galaxy which is a barred spiral. We have a bar too sitting in the center, which you can see over here. And you can see there are various spiral arms which have been marked over here on this image. So there are various spiral arms of the galaxy, and you have the sun belonging to sitting over here, right? So here I have another cartoon of our galaxy. This is another galaxy which looks like what we think Milky Way would look like, but is obviously not the Milky Way. And if we look at it through edge on, that means we look at it across the thing, it is more of a flattened kind of a structure. So what you can actually see is there's a disk, the blue disk, which you can see over here. The orange part, which you can see, is the bulge of the galaxy. The outer region is what is called the halo. The halo basically has the globular clusters that we spoke about earlier in terms of Shapley. And the galaxy center here is marked in pink. So what you see is that the Milky Way has three major components: the bulge, the disk, and the halo. Now, what is the disk? The disk has a thickness, it's a thin disk, and therefore the disk has a thickness of only 1 kpc, and it contains various kinds of stars, nebulae, OB regions, various kind of bright objects. You know that the disk is very bright. It has spiral arms, and spiral arms are blue. They are made up of very young stars, and therefore you can actually use spiral arms or star formation in the galaxy can be used to actually trace the positions of the spiral arms of the galaxies. The halo region is what we call the outer part, which we had marked over there. And the halo is basically made up of older stars. These older stars are also called population 2 stars because they are the older ones. And the present stars, that is the stars which belong to the disk, are called the population 1 stars. And these are basically the stars which are found in globular clusters. And like I said, these are older stars. So if you actually look at the galaxy like this over here, you have the halo, disk, and bulge. And the disk is basically where you have the population 1 stars, which make up the spiral arms. They are young metal-rich stars. While the halo has the populations 2 stars, which are old stars, and they are metal-poor stars. Now let us try to recollect when we spoke about stars. We said stars basically do nuclear fusion, right? So older stars, they the ones that formed much earlier, they have much lesser amount of heavier metals. While the younger stars, these are population 1 stars, these are actually later generation stars, formed from the residues of the earlier generations, and hence the population 1 stars are more metal enriched. That is, they have a larger amount of heavy metals present in them. So here I have another picture which you can see the bulge and the disk and the halo. The halo is a much larger component of the galaxy. Now let's talk about star formation. Now what we know is that 70% to 90% of the stars are actually formed in what we call embedded clusters. By embedded we mean they are clusters which are within gas and dust. And some of them are actually stay bound and they evolve to form what are called open clusters, and the remaining they disperse and contribute to the galactic field. So as per our understanding, even the sun should have formed in some such cluster, and then the cluster later on dispersed off, because the sun is already 4.5 billion years ago. So the cluster probably dispersed. So half of the stars in the sky actually have stellar companions which are bound by gravity, and hence we can see that multiplicity is actually the norm. So a star cluster is basically what our understanding of stars formation, which we spoke about yesterday is also, is that stars do not form in isolation. They typically form in clusters because it's only very big molecular clouds which can satisfy the Jeans criterion. So hence you have to have a very massive cloud to satisfy Jeans criterion, and the massive cloud will form a large number of stars once it starts a gravitational collapse. So once this molecular cloud starts a gravitational collapse, it forms a whole set of stars, which actually leads to what is called a star cluster or a group of stars. And these star clusters are basically a sample of stars formed from the same molecular cloud, where all the stars have the same age, chemical composition, and at the same distance. They only differ in mass. And there are basically 2 types of clusters. What you see over here down is called an open cluster, and what you see on the right over here is a globular cluster. A globular cluster is much more massive and it has a much more dense setting of stars. The other kind is what is called associations. Associations are clusters which actually dispersed at a very early stage. So globular clusters, these are the clusters which basically make up the halo of the galaxy. The halo of the galaxy is made up of, like I mentioned earlier, population 2 stars. These are older stars, and they are basically red stars. Red stars are stars which are older and very old stars. So most of these stars are at least 10 billion years old. Globular clusters are 10 billion years old. And yesterday when we spoke about HR diagrams and stellar evolution, so we actually use those HR diagrams to actually get the ages of globular clusters. And hence we know that globular clusters have ages of about 10 billion years. And like I said, the stars are red and old. Open clusters, in contrast, are a much more loose grouping of stars, where the number of stars are much lesser, but the stars are younger. So they are basically blue. And again, by using the HR diagram, we can find the age of open clusters, and most open clusters, the bound ones, have ages of 10 power 6, that is a million years, or 100 million years, that is 10 power 8. And these basically are close to the plane of the Milky Way, and they are spiral arm tracers. And these have regular planar orbits as they're going around the galactic, in the galactic disk. So I just wanted to mention this open cluster, which most of you can actually see with your naked eye. This is called Pleiades, which is in Taurus, and it actually it is also called Kritika in India. And it's pretty easy looking up at this thing. If you can see the Taurus constellation, you can actually see it quite easily. Associations, like I mentioned earlier, these are groups of stars which did form exactly like star clusters from the same molecular cloud. The only difference is that they start dispersing. They started dispersing at a much earlier stage compared to normal open clusters. And therefore, you have these set of OB type of stars that are very hot young stars, where actually if you measure their velocities and you retrace it, you can realize that they all came from a certain convergent point, right? And these are typically, again, on the plane of the galaxy because they are young, and they are prodigious sources of energy because these stars are typically O-type or B-type stars. That is, they are very hot stars, and hence they emit very strong stellar winds and ionize the ISM. So that is the disk of the galaxy and the halo of the galaxy that we spoke about. The other interesting component of the galaxy is the galactic center, which is in the bulge. So if you want to actually find the galactic center, this is the Sagittarius constellation, which actually looks like a teapot, if you can identify it in the sky. Scorpius is also a very easy constellation to identify in the sky. It looks like an inverted question mark. And somewhere between this part, you'll actually find this is the region, which is the galactic center. So you can see in the background over here, you can see this haze over here, and you can see there's a slight darkening. And that's because towards the galactic center, there's a very large amount of gas and dust. You can see this part being a little darker, right? And that is why there's a problem in actually looking at the galactic center, because there's a lot of gas and dust in that direction, which actually obscures our viewing of the galactic center. So like I mentioned, the galactic center is in the direction of Sagittarius, and there's obviously lots of gas moving around. And what we actually have is that you have a massive black hole, which is sitting at the center of the galaxy. Now, how do we actually see the black hole? Here I have an image of the galactic center, which is using radio data. Like I mentioned, extinction is the problem which stops our viewing of the galaxy. But the advantage is that the extinction is inversely proportional to wavelength. So therefore, at longer wavelengths, you have much lesser extinction. And therefore, if one wants to look at the galactic center, you need to look at longer wavelengths. So that could be, for example, the infrared or the radio. So this is an image using the Very Large Array, which is a radio telescope, to actually image the center of the galaxy. So this is an image of the center of the galaxy using radio data. Another very good way of looking at the center is also using X-rays. And X-rays are very high energy sources, and therefore you can actually penetrate through the center and see it. So there's an X-ray telescope called Chandra. We'll talk about it on the last day. And this is an image of the galactic center where you can actually look at it. And the galactic center is located near a very small point source, which is called Sagittarius A star. And this is the point which is the galactic center. Now, most galaxies have supermassive black holes at their centers. And even our galaxy does have a massive black hole at the center. So if you actually see this image over here, here is a star which is called S2, which is a star which is located very close to the galactic center. And this star over here, what has been done is that it actually goes around the black hole at an amazingly large speed. So if you can see over here, it actually goes at the speed of 5,000 kilometers per second, right? So very laborious observations were made of the S2 star in the infrared to actually look at so this was, you have a 16-year period. So this crossed closest to the galactic center on 19th of May 2018. And after that, it went past the galactic center. And basically, this large velocity which it has is basically because of the presence of the massive black hole, which is sitting, supermassive black hole, which is sitting over here. So what was done is very meticulous observations were made of the movement of S2 to actually measure the mass of the galactic black hole. Also, this was a very good example or a good demonstration of relativity and how do relativistic effects, because relativistic effects because of the massive black hole would be very large in this region. And therefore, it was also used to actually test principles of relativity. Okay, so like I mentioned over here, there are these various stars which are going around the galactic center. And Sagittarius A, like I said, it has a 16-17-year-old period. It was observed, and with that it was derived that the mass of the black hole is about 4.31 million M-sun. So 4.31 into 10 power 6 times the mass of the sun. And that is what actually drives S2 to move at this crazy speed of 5,000 kilometers per second. Another interesting aspect of our galaxy is what is called rotation curves. That is, if you look at stars from different distances from the center of the galaxy, you can actually make a plot of the velocity of those stars versus their distance from the center. Now I'll repeat, okay, I can see it over here. So if you actually take the center of the galaxy over here and you plot the velocity of stars as they move away from the center. Now you'll see in the central region, you'll see a direct, almost a straight line thing. This is V, this is R. So it's like V is equal to omega R. This is like a straight line plot. So this is exactly how you would have a solid body rotating, right? A solid disk, for example, would rotate exactly in that kind of a way. That is, you will have the linear velocity would be directly equal to omega times R, right? So that means it would be directly proportional to R, which is the straight line. Now, if the stars were to move, like, for example, by Kepler's law, you basically have a 1 upon r squared kind of dependence, and therefore your velocity as you go to the outer regions will actually fall. So if you actually had Kepler's laws, like if you actually do that for the planets of our solar system, you will actually see that the velocity falls in the form of this curve, this white curve. But what we actually see is that when we observe with stars itself, the yellow points which you have over here, you can see the curve goes something like this. And then if we take the outer regions of the galaxy, we observe it, this is using the 21 centimeter hydrogen line. This is in the radio region of the electromagnetic spectra. And we can use that also to derive the velocity of the 21 centimeter line of hydrogen over here. And we actually get a curve like this, okay, which is very different from what we would have expected. Because if we were just following Kepler's laws, we would expect a fall of this kind. But what we actually get is something that looks like this. That is, strangely, as you're going to the outer regions of the galaxy, instead of stars slowing down, they actually seem to fasten up. That means stars which are further away from the center, they are moving faster than the ones which are closer from the center. If you remember when we spoke about Kepler's laws, we spoke about stars that when they were closer to the center, planets, when they were closer to the sun, they were actually moving much faster compared to when they were further away. That's Kepler's laws, which is this plot, which is the white line you can see. But what we actually observe is something like this, which is the reverse. That is, as you're going outside, your velocities are increasing. Now, if all the mass was sitting in the center of the galaxy, then in that case, you would have expected Kepler's laws. But the very fact that this is going around in this way implies that there is mass on the outer parts of the galaxies, which are causing these stars to move so fast. Now, people could not understand what kind of mass could there be there, which could actually cause these stars to move so much faster. And therefore, not very creatively or not very imaginatively, people decide to call that dark matter. Okay, so dark matter, it is basically dark for the simple reason is that we do not see it in terms of stars. There's no material we can see it. It's not visible to us, but we can see it in the term of its gravitational effects. In the sense, it is causing, the gravitational law is actually causing these stars to move faster. So dark matter actually influences that region gravitationally. And actually, if you make an estimate for how much of dark matter is required for the given rotation curve, even for the Milky Way, you'd see that 90% of the Milky Way mass is the dark matter mass. Okay, so you typically have galaxies which are actually sitting in what are called dark matter halos. So you have these blobs over here, and you have the galaxy sitting right in the center of these dark matter halos. And these dark matter halos are basically 90% of the galaxy, which are outside, and the visible part of the galaxy is just the central part, while this huge dark matter halo is actually causing the motion of those stars. If you look at the local neighborhood, yeah, so that's the galactic center. We'll go back to the local neighborhood of our galaxy. You see that this is our galaxy. We have two satellite galaxies. One is called the Large Magellanic Cloud, and the other one is called the Small Magellanic Cloud. And it's not just this. If you actually look further around, you'll actually see we have a whole set of satellite galaxies which all seem to be going around the Milky Way. And if you remember the talk that Hassan sir gave you about galactic interactions, what is considered is that these were all galaxies which were kind of eaten up by the Milky Way. So the Milky Way kind of ate up these galaxies, disrupted them, due to which we have these different stellar streams of stars which are there, which are not very dense, but they are caused by the presence of these different satellite galaxies, which are also marked in this image over here and in this image over here. Now, we'll wind up with what's going to happen to the fate of our galaxy. What's going to happen to our galaxy? Now, the closest galaxy next to us is a galaxy called Andromeda. And you can see in this video over here, which I'll show you very soon, that you can see that the Andromeda and galaxy and the Milky Way are actually on a collision phase. Okay, they are on the verge of, they are actually to collide with one another. And if you were to actually see this video, I'll try to run it, and it doesn't want to run. So you can actually see that this galaxy is actually coming head on onto us, Andromeda, and the two galaxies, Milky Way and Andromeda, are on a straight collision path, right? So I'll show that to you over here, and let's hope it comes. So it doesn't seem to want to come. And okay, so I'll let's go back to this. And so if we come onto this, like what I told you was, these two galaxies are on a total head-on collision. That's what they are going to be up to, right? So you can see that the collision would take after 4.5 billion years, and they'd merge to actually form an elliptical galaxy. The resultant would be, let's call it the Milkomeda or the Milkodromeda, and this resultant object which we have, it would be a huge lenticular galaxy which we'd get from the merging of Milky Way and Andromeda. And roughly about 150 billion years from now, the remaining galaxies also of the local group will coalesce into this object, and that would be the next evolutionary stage of the local group of galaxies. So basically it gives us an idea of how galaxies move from small to big. You have merging of smaller galaxies causing larger galaxies. I will end with mentioning what is called Gaia. Gaia is a very new satellite of the ESA, the European Space Agency, which actually does very accurate measurements of the positions and velocities of stars. And that's what Gaia is actually doing. It's actually measuring these positions for 1 billion stars. And hence you can actually check out a lot of news briefs on the new developments that we know about the galaxy thanks to the Gaia mission. And I'll end with that. So look out for posts about Gaia and how Gaia has been discovering more new things about our galaxy. And yeah, so we'll end up with that. And